For the Hux-Wacker process, we are given the following equation. So acetaldehyde is being produced via the following equation. C2H4, two of them reacting with oxygen to form two molecules of acetaldehyde. And also given to us is the fact that the Hux-Wacker equation, Hux-Wacker process is an exothermic reaction. So with all of that given information, we can then surmise the following when we introduce the following disturbances. So for letter A, when we remove the acetaldehyde as it is being formed, what will happen is then the following. So by removing the acetaldehyde as it is being formed, we are forcing the equilibrium to shift further and further to the right. Sorry. And as it shifts to the right, more and more of the acetaldehyde will then be formed. Letter B, by adding some inert gas into the reaction vessel, will not affect the equilibrium in any way. So therefore, the amount of equilibrium that will not be formed will not be affected. Now, since the Hux-Wacker equation is an exothermic reaction, increasing the temperature would then disturb the system in such a way that the equilibrium shifts to the side where less heat is being formed. So the equilibrium actually shifts to the left. And as that happens, some of the acetaldehyde is being used up to be able to reform our C2H4 and the oxygen, so that ultimately there should be less acetaldehyde that will be obtained. Now for the opposite scenario, by decreasing the temperature of the reaction vessel, we force the equilibrium to try to form more heat so as to minimize the effects of the external stressor that we have put upon it. And so our equilibrium will then shift to the right. And as it does so, more of the acetaldehyde will then be formed. And finally, carrying out the oxidation over a homogeneous palladium copper catalyst speeds up the reaction and the rate at which equilibrium is attained, but it does not affect the equilibrium in any way. So it only manages to speed up the reaction. That's the only effect that the catalyst